We tend to assume that when the last star finally burns out, the universe simply falls into darkness and the long story of light is over. But that is not how it ends. The smallest, faintest stars will go on burning for 10 trillion years after the bright ones are gone. And after even they fade, the darkest objects in all of existence, black holes, become the final sources of light, glowing faintly for as long as 10 to the 100th power years before flaring out one last time. Even then, the light they made does not stop. It keeps going, stretched longer and colder, with nothing left to catch it. Because light, it turns out, does not end the way everything else does. Get comfortable. Subscribe if this is your first time, because by the end of this, the word darkness will not mean what you think it means anymore. Let's slowly slip into this. Part 1. The light you stopped noticing. There is a kind of light around you right now that you almost certainly stopped noticing a long time ago. Maybe it is the warm glow of a lamp in the corner of the room. Maybe it is the cooler light of the screen you are listening through, or a candle, or the pale silver of the moon coming in through a window. Whatever it has been there so reliably your whole life that your mind has quietly filed it away under the category of things that simply are. Light is just there. It fills the room when you want it to. It crosses the gap between a star and your eye without asking anything of you. It seems like the most ordinary, the most permanent, the most harmless thing in the entire world. Think about how rarely you actually look at light itself, rather than at the things it lets you see. You use it constantly, every waking second, and yet it is almost perfectly transparent to your attention. You notice the lamp, not the light from the lamp. You notice the face of someone you love, not the stream of photons carrying that face to your eyes. Light is the one thing always present and almost never seen, the medium through which everything else arrives, so woven into the act of seeing that it disappears into it. And because it is always there, always reliable, always free, we file it away as a thing that does not need explaining, a fact of life as basic as the ground underfoot. Tonight I want to gently lift it back into view and ask of this most familiar thing the most unfamiliar question there is. I want to begin tonight by gently taking that assumption apart, because it is wrong in almost every way that matters, and the truth underneath it is one of the strangest and quietest stories that physics has ever told. Light is not permanent. Light has a history as real as the history of any star or planet. It was born, in a literal sense, almost 14 billion years ago, in an event we can still detect today. And the universe that light travels through is changing, slowly and relentlessly, in a way that has a direct and permanent effect on every single particle of light in existence, including the ones reaching your eyes in this very moment. So here is the question we're going to follow all the way to its end tonight. And I mean its actual end, the farthest edge of time that physics can describe. What happens to light at the end of time? Not the end of a candle, when the wax runs out. Not the end of a day, when the sun goes down. The real end. The point almost unimaginably far in the future, when the stars have all gone dark, when the galaxies have vanished from the sky, when the last sources of new light in the universe have burned themselves out. What happens to the light then? Does it stop? Does it die? Does it simply keep going forever into a darkness with nothing left to shine on? The honest answer is more beautiful and more disorienting than any of those, and getting to it is going to take us on the longest journey this channel has ever attempted. We are going to travel not across space, the way we usually do, but across time. We are going to start at the very first instant that light could move freely through the universe, and we are going to follow a single particle of that light forward, through the birth and death of stars, through the slow emptying of the sky, through eras so far in the future that the entire age of the universe so far is less than the blink of an eye by comparison. And along the way, the light in the room around you is going to stop looking ordinary and start looking like the most remarkable thing you have ever failed to notice. Before we can go anywhere, though, we have to be honest about what we actually mean by the word light, because almost everyone carries a slightly wrong picture of it in their head. We tend to imagine light as a kind of stuff, a glowing substance that pours out of bright things and pools in bright places. That picture is good enough for everyday life, but it hides the real nature of the thing, and the real nature is where every strange consequence in this entire story comes from. So that is where we have to start. Not at the end of time, but with the simple, almost impossible question of what a single particle of light really is, and why it behaves utterly unlike anything else in the universe. I should warn you, kindly, that this is going to be a slow journey, and that is on purpose. We are not in a hurry tonight. There is no breaking news to rush toward, no countdown, no urgency. The end of time is not going anywhere, and neither are you. So settle in, get comfortable, and let your attention go soft. If you drift off somewhere in the middle, that is perfectly fine. The story will still be here, and so will the light. Let us begin, as all light begins, with the smallest possible piece of it, and let us see just how strange that small piece turns out to be. Part 2. The one thing that never ages. Light is made of particles called photons, and a photon is unlike almost anything else in nature. To understand everything that happens at the end of time, you only need to hold on to a few facts about photons. But these facts are so strange that most people, hearing them for the first time, assume they have misunderstood. They have not. The strangeness is real, and it is the foundation of this whole story. The first fact is that a photon has no mass, not a very small mass, not a mass too tiny to measure. As far as every experiment ever performed can tell, a photon has exactly zero mass, and the best measurements we have place any hidden mass it might secretly carry below a limit so small it is hard to even write down, less than a billionth of the mass of a single electron, which is already one of the lightest things that exists. For all practical purposes, and for all the purposes of tonight, a photon weighs nothing at all. The second fact follows from the first, and it is the one that begins to bend the mind. Because a photon has no mass, it always travels at exactly one speed, the speed of light, which is about 300,000 kilometers every second. It is not that a photon can go that fast. It is that a photon can only go that fast. It is born moving at that speed. It travels at that speed for its entire existence, and it never slows down, never speeds up, never rests. The moment a photon comes into being, it is already moving as fast as anything in the universe can possibly move, and it stays that way until the instant it is absorbed by something and ceases to be. Now, hold those two facts together, because the third one comes out of combining them with Einstein's relativity, and the third one is where the real wonder lives. One of the things relativity tells us is that the faster something moves, the slower time passes for it, compared to the world around it. This is not a trick or an illusion. It has been measured countless times. A clock on a fast-moving aircraft really does tick a tiny bit slower than a clock on the ground. The faster you go, the more pronounced this becomes. And here is the question that opens the door to everything. What happens to time for something moving at the absolute speed limit of the universe, the speed of light itself? The answer is that time stops. For a photon, no time passes at all. From the photon's own frame of reference, the moment it is created and the moment it is absorbed are not separated by any time whatsoever, no matter how far apart they are for the rest of us. A photon that leaves a distant star and crosses billions of years of space before landing in your eye does not experience billions of years. It does not experience millions or thousands, or seconds. It experiences nothing. Its birth and its death are, for the photon, the same single instant, touching, with no gap between them at all. I want you to sit with that, because we are going to return to it at the very end of tonight's journey, and when we do, it is going to mean something far heavier than it does right now. From light's point of view, no time passes at all. Say it quietly to yourself once. A photon does not travel through time the way you and I do. It does not age. It does not get older, or wear out, or grow tired on its long journey. The photon that has been crossing the universe since almost the beginning of everything is, from its own perspective, exactly as young as the instant it was born. There is one more fact, and it completes the picture. In the standard understanding of particle physics, the framework that describes all the known particles and forces with extraordinary precision, the photon is perfectly stable. It does not decay. Many particles in nature are unstable. Leave them alone, and after some characteristic span of time, they spontaneously fall apart into lighter particles. A free neutron, drifting on its own, will last only about 15 minutes before it breaks down, but a photon, left alone, lasts forever. It has no built-in expiration. Nothing inside it counts down. In the absence of something to absorb it, a photon simply continues, ageless and indestructible, at the speed of light for as long as the universe allows. I should add one honest caveat here, because it is the single thread by which light could, in principle, be made mortal, and we will want it later. Everything I have just said rests on the photon being truly massless. If it turned out that the photon has a tiny mass after all, some impossibly small amount hiding just below the limit of what we can measure, then a few things would quietly change. It would no longer travel at exactly the speed of light, only very nearly. It would experience a sliver of time rather than none at all. And, most importantly, it would become possible for the photon to decay, to fall apart into even lighter particles, the way other unstable particles do. Physicists have actually worked out what this would imply. One careful study, published in 2013, found that if the photon does carry a mass, then a particle of visible light would have to survive for at least about 1,000,000 trillion years before decaying, an enormous span, far longer than the current age of the universe, but not infinite. In that scenario, light could in fact die of old age, dissolving into the faintest particles in nature after an unthinkable wait. I want to be clear that every experiment ever done is perfectly consistent with a massless, immortal photon, and that is the picture we will use tonight. But the door to a mortal photon has not been completely closed, and it is worth knowing that the immortality of light, like almost everything in this story, rests on a measurement we are still, even now, trying to push a little further. So here is the strange thing we now have to confront. We started tonight by asking what happens to light at the end of time, and we have just learned that light has no mass, ages not at all, and does not decay. By every measure we have, a photon is immortal. It is, quite possibly, the single most durable thing in all of nature. And yet we also know, from simply looking at the sky, that light clearly does change. The light from distant galaxies arrives stretched and reddened. The oldest light in the universe, which we will meet very soon, was once blazing hot and is now barely warmer than absolute zero. Something is happening to these immortal, ageless photons. Something is changing them, even though they cannot age and cannot die. The question is, what? And to answer it, we have to go back to the very beginning, to the first light that ever flew free, and watch what the universe itself does to it over the long ages that follow. That first light is still out there. In fact, it is all around you, and it is the oldest thing you will ever encounter. Part 3. The first light. To find the first light, we have to travel back almost to the beginning of the universe, but not quite. We have to stop at a very particular moment, about 380,000 years after the universe began. And to understand why that moment matters, we have to understand what the universe was like before it. In its earliest ages, the universe was not the cold, clear, mostly empty space we know today. It was unimaginably hot and unimaginably dense, a furnace filling all of existence, far too hot for atoms to hold together. Everything was broken down into its smallest pieces, a glowing soup of bare atomic nuclei and free electrons, all of it crammed together and seething. And in this state, light could not travel. This is the part that surprises people. The early universe was blindingly bright, full of energy, full of photons, and yet it was completely opaque because a photon could not get anywhere. Every time a particle of light tried to move, it almost immediately ran into one of those free electrons and bounced off in a new direction. The universe was a fog, a glowing fog, where light was trapped, scattering endlessly, never able to fly in a straight line for long. Picture it as a kind of cosmic morning mist, except the mist itself is on fire, glowing from within, and every ray of light is bounced around inside it so many times that it can never escape. For 380,000 years, the universe stayed like this, a bright, hot, trapped haze. And then something changed, gradually but inevitably, as the universe expanded and cooled. The temperature dropped to about 3,000 degrees. That is still hot, hotter than molten metal, but it was the crucial threshold, because at 3,000 degrees something new became possible. The free electrons finally slowed down enough to be captured by the atomic nuclei, settling into orbits around them, forming the first complete, stable, neutral atoms. Hydrogen, helium, the first ordinary matter. This moment, when the fog cleared and light flew free, is special for another reason, and it gives the first light a kind of authority nothing else can match. It is the farthest back we can ever see. Before this moment, the universe was opaque, so no light from any earlier time can reach us directly, because no light could travel freely then at all. The instant of clearing is therefore a wall to our vision, the surface beyond which we simply cannot look with light, no matter how powerful our instruments become. We call it the surface of last scattering, the place where the first light last bounced off a free electron before flying clear. Whenever we detect the first light, we are looking at that wall, seeing the universe as it was at the single oldest moment light can show us. Everything earlier is hidden behind the fog forever. The first light is not just old, it is the edge of the visible past itself. And the instant that happened, the fog lifted. With the electrons now bound up inside atoms instead of roaming free, there was suddenly nothing left to block the light. The photons that had been trapped, scattering endlessly for 380,000 years, were abruptly set free. For the first time in the history of the universe, light could fly in a straight line across open space. And it did. All of it. Everywhere. All at once. This is the moment I want you to witness, because it is the birth of the first light, the oldest light there is, the light we are going to follow for the rest of this journey. Imagine you are floating inside the universe at the instant it happens. All around you is a dense, glowing haze, the colour of a dull, dying ember, a sullen orange-red, and it is so thick that you cannot see your own hand if you held it in front of you, because any light it gave off would be scattered away before it reached you. The whole of existence is this featureless, glowing fog, pressing in from every direction, 3,000 degrees, humming with trapped energy. And then, everywhere at once, in every direction, the haze begins to clear. It does not happen in one place and spread. It happens everywhere simultaneously, the entire universe turning transparent in the same long moment. The orange glow thins and softens, and suddenly you can see. Light is moving now, streaming, pouring across newly opened space in every direction, free at last after being trapped since the beginning. Pick one of those photons, a single particle of that first light, leaving the cooling haze and setting out across the universe. It does not know it, because it knows nothing, but it has just begun a journey that will outlast the stars, the galaxies, and very nearly everything else that will ever exist. That light has a name today. We call it the cosmic microwave background, and it is not a metaphor or a faint historical trace. It is real, it is measurable, and it is genuinely all around you right now. The light released in that moment, 380,000 years after the beginning, has been traveling ever since, and a great deal of it is still traveling, still crossing space, still arriving. If you point a sensitive enough radio antenna at the sky, in any direction at all, you will detect it. It fills the entire universe. There are, on average, around 400 photons of this first light in every single cubic centimeter of space, including the cubic centimeters in the room around you. For every atom of ordinary matter in the whole universe, there are roughly 1 billion of these ancient photons. They outnumber everything. The first light is, by an overwhelming margin, the most common light there is. We did not always know it was there. The story of how we found it is almost comic. In the 1940s, a few physicists working out the consequences of a hot early universe predicted that there should be a faint afterglow left over from it, a relic radiation filling all of space. The prediction was largely forgotten. Then, in the mid-1960s, two researchers named Arno Penzias and Robert Wilson, working at a laboratory in New Jersey, were trying to use a large horn-shaped antenna for radio astronomy, and they kept picking up a faint, persistent hiss coming from every direction in the sky. They could not get rid of it. They checked their equipment for faults. They even cleaned out the droppings of pigeons that had been roosting in the antenna, suspecting the mess might be the source of the noise. Nothing made the hiss go away, because the hiss was not a fault. It was the first light of the universe, the relic glow predicted years earlier, arriving from every direction at once. They had accidentally detected the oldest thing anyone has ever found. The discovery would later earn a Nobel Prize. In the decades that followed, we learnt to read that first light with extraordinary care, and what it told us deepened the wonder rather than dimming it. A satellite, launched at the end of the 1980s, measured the spectrum of the first light precisely enough to confirm that it is the most perfect example of a particular kind of glow, called a blackbody glow, ever found anywhere in nature, exactly the kind of even, thermal radiation you would expect from a universe that was once a uniform hot fog. But the same measurements revealed something else, almost hidden in the smoothness. The first light is not perfectly uniform. Across the sky, its temperature varies, ever so slightly, by about 1 part in 100,000, faint patches very slightly warmer and very slightly cooler than the average. Those tiny ripples are not noise, they are the seeds of everything. The slightly denser regions, marked by those minuscule temperature differences, are the places where gravity would later gather matter together into the first stars, the first galaxies, the great structures that fill the universe today. Later, missions mapped these ripples in finer and finer detail, and from that map we have measured the age, the composition, and the shape of the cosmos. So, the first light is not only the oldest light, it is also a baby photo of the universe that carries, written in its faint pattern of warm and cool, the blueprint of every galaxy that would ever form, including the one we live in. So we have our protagonist now, a single photon of the first light, born in the clearing fog 380,000 years after the beginning, set free to cross a universe that is just learning how to be transparent. It is ageless, it weighs nothing, and as far as the laws of physics are concerned, it will last forever. And yet, over the long ages that follow, something is going to happen to it. Not all at once, but slowly, continuously, for billions of years. By the time it reaches us, it will have changed almost beyond recognition, even though it has not aged a single instant. To understand what changes it, we have to ride along with it and watch what the universe does to a particle of light over the longest spans of time. That is where we go next. Part 4. The long stretch. Let us ride alongside our photon now, the single particle of first light, and watch what happens to it as the ages pass. To do that, you have to set aside the idea that the photon is going on a journey through a fixed, unchanging space, like a traveller crossing a country that stays the same beneath their feet. That is not what is happening. The space the photon moves through is not staying the same at all. It is growing. The entire universe is expanding, every region of it swelling outward, the distances between things stretching wider with every passing age. And this single fact, that space itself is getting larger, is the key to everything that happens to our photon and to all light for the rest of time. When we say the universe is expanding, people often picture the galaxies flying apart through space, like fragments hurled outward from an explosion. That picture is misleading. The galaxies are not, for the most part, rushing through space away from each other. It is the space between them that is growing, swelling, lengthening, carrying them apart, the way raisins in a rising loaf of bread are carried apart by the dough expanding between them. The raisins are not moving through the dough. The dough itself is getting bigger, and the raisins simply go along for the ride. Space is the dough. The galaxies are the raisins. And our photon is something travelling through the dough while the dough itself stretches. It is worth saying plainly that this stretching happens to all light, not only to the first light we are following. Every photon from every star, every beam that has ever crossed a meaningful stretch of the expanding universe is reddened by the same process. The light from a distant galaxy arrives at our telescopes shifted toward the red exactly because it, too, has had its waves drawn out by the growth of space during its long crossing. The farther away a galaxy is, the longer its light has been travelling, the more the space has stretched in the meantime, and the redder its light arrives. This is one of the central tools of astronomy, the way we measure the distances and the motions of things across the cosmos. But for tonight, it means something simpler and more sweeping. The fading we are tracing is not a special fate reserved for the relic glow of the beginning. It is the fate of all light everywhere, written into the very fact that the universe is growing. So picture the photon as a wave, because light is also a wave with a certain wavelength, a certain distance from one crest to the next. When that wave travels through space, and the space itself is stretching, the wave gets stretched along with it. The crests are pulled farther apart. The wavelength grows longer. And here is the crucial thing about light. A longer wavelength means a redder colour and a lower energy. A wave stretched out long and slow carries less energy than a wave packed tight and quick. So as our photon crosses the expanding universe, age after age, its wavelength is drawn out longer and longer, and its colour slides down the spectrum, and its energy quietly falls. This process has a name. We call it the cosmological redshift. Redshift because the stretching moves light toward the red, lower energy end of the spectrum, and cosmological because the cause is the expansion of the cosmos itself. And I want to be very precise about what is happening, because it is easy to get wrong. The photon is not slowing down. It cannot slow down. It is still moving at exactly the speed of light, as it always has and always will. The photon is not getting tired. It is not losing energy to friction, or wearing out, or weakening from the effort of its long flight. None of those things are happening. The only thing happening is that the space the photon lives in keeps getting larger, and the photon's wave is stretched out longer as a result. The change is not in the light. The change is in the universe the light is passing through. You might reasonably wonder whether there is a simpler explanation for all this reddening, one that does not require the whole of space to be stretching. Perhaps, you might think, the light really is just getting tired. Perhaps a photon, crossing billions of years of space, slowly loses a little energy along the way, growing redder with distance the way a runner slows over a very long race. This is not a foolish idea. In fact, it was proposed in earnest back in 1929, and it has a name, the tired light hypothesis. The trouble is that it does not survive contact with the evidence. If light lost energy gradually by bumping into something as it travelled, that same something would also blur and scatter the images of distant galaxies, and yet those images come to us sharp and clear. The tired light idea also predicts the wrong relationship between how far away a thing is and how bright it appears. And most decisively of all, when we watch distant, exploding stars, we see their light not only reddened, but also slowed and stretched out in time, exactly the way the stretching of space predicts, and exactly the way a simple loss of energy does not. The redshift is real, and it is the stretching of space. Light is not getting tired. The space it lives in is getting larger. There is a question that troubles many people when they first really understand the redshift, and it is a good question, sharp enough that it took physicists a while to make peace with it. If every photon in the universe is losing energy as its wave is stretched, where does that energy go? Energy, we are taught, is supposed to be conserved. It cannot simply vanish. And yet the first light today carries only about 1,000th of the energy it had when it was born, and that fraction is still falling. So where did the lost energy go? The honest and surprising answer is that it did not go anywhere. On the scale of the whole universe, energy is simply not conserved in the way our everyday intuition demands. The rule that energy must be conserved comes from the laws of physics, staying the same from one moment to the next, and in an expanding universe, where the geometry of space itself is changing with time, that condition does not strictly hold. The energy lost to redshift is not transferred to some other place or some other form. It ceases to be. This is not a flaw in our understanding or a bookkeeping error. It is a real and underappreciated feature of how the universe works, and it means that the fading of light is, in the most literal sense, energy quietly leaving existence as the cosmos grows. Let us watch it happen to our photon. It was born in the clearing fog at about 3,000 degrees, which means it started out as a particle of visible and infrared light, glowing in that sullen orange-red. As it sets out across the young universe, the space around it begins to stretch, and its wavelength begins to grow. Eons pass. The first stars ignite somewhere in the distance, gathering out of the cooling gas, but our photon flies on, indifferent, between them. Galaxies begin to assemble, great wheels of light slowly turning, and still the photon travels, and still its wave is drawn longer. Its colour fades from orange toward red, then past red into the infrared, the band of light we feel as heat but cannot see. The universe keeps swelling, the photon keeps stretching. Here is the immersive truth of it, if you ride along. You are moving at the speed of light, the fastest anything can go, and yet you have the strangest sensation of being slowly drawn out, lengthened, like a single long note held so far past its natural end that it slides downward in pitch, lower and lower, with no bottom in sight. Below you, in the immense slow drift of the ages, galaxies condense out of the darkness, spin through their long lives, and slide past and away. Whole generations of stars are born and die in the time it takes you to cross a single region, and none of it touches you. You do not feel the eons. You do not feel anything, because no time is passing for you at all. It is the universe around you that ages, that builds its galaxies and stretches its space, while you, the photon, remain exactly as young, as the moment the fog first lifted. You are simply being unwound, your wave pulled longer and cooler by a cosmos that will not stop growing. By the time our photon has crossed nearly 14 billion years of this stretching space and arrives at a small blue planet, at a radio antenna, at a detector, it has been transformed. The wave that started out at 3,000 degrees of glowing orange-red has been stretched more than 1,000-fold. Its wavelength, once short enough to be visible, is now around a millimeter long in the band we call microwaves, the same kind of light a microwave oven uses, though incomparably fainter. Its temperature, which is just another way of describing the energy of the light, has fallen from 3,000 degrees all the way down to about 2.5 degrees above absolute zero, the coldest temperature there can be. This is why we call it the cosmic microwave background, and not the cosmic visible light background. The first light was not born as microwaves. It was born as a hot orange glow, and the expanding universe has spent 14 billion years stretching it down into the cold, faint, invisible whisper we detect today. I find something quietly moving in this, and I want to name it before we move on. The oldest light in the universe, the first light that ever flew free, has been fading and cooling this entire time for nearly 14 billion years, and it is fading and cooling still. It did not stop when it reached us. The photons we detect are simply the ones that happen to arrive now. Countless others are still out there, still crossing space, still being stretched longer and cooler with every passing age. The first light has been dying, in the gentle sense we are going to keep returning to tonight, since almost the beginning of everything. And it is not finished, because the universe is not finished expanding. In fact, the expansion is about to do something that will change our photon's fate, and the fate of all light, far more dramatically than anything it has done so far. The stretching is not staying steady. It is speeding up. And to understand why that matters so much, we have to talk about the strangest ingredient in the universe, the thing that is taking the sky apart. Part 5. The sky begins to empty. For most of the 20th century, scientists assumed that the expansion of the universe must be slowing down. This seemed almost obvious. The universe was full of matter, and matter has gravity, and gravity pulls things together. So however fast the universe had started expanding, all that mutual gravitational attraction should be acting like a brake, gradually slowing the expansion over time, the way a ball thrown upward is slowed by the pull of the Earth. The only real question, people thought, was whether the brake was strong enough to eventually stop the expansion and reverse it, or whether the universe would coast outward forever, slowing but never quite stopping. In the late 1990s, two competing teams of astronomers set out to measure exactly how much the expansion was slowing down. They did it by studying a particular kind of exploding star, a type of supernova that always explodes with very nearly the same true brightness, which makes it useful as a kind of cosmic mile marker. By comparing how bright these explosions appeared with how far away they actually were, the teams could measure how fast the universe had been expanding at different points in its history. They expected to find the expansion gradually slowing. What they found instead, in 1998, was the opposite, and it was so unexpected that both teams spent a long time looking for mistakes before they believed it. The expansion of the universe is not slowing down, it is speeding up. For the first several billion years, gravity did act as a brake, and the expansion did slow. But then, around 6 billion years ago, something took over, some force pushing outward, overwhelming the inward pull of gravity, and the expansion began to accelerate. It has been accelerating ever since, faster and faster, and as far as we can tell, it will keep accelerating without end. This discovery was so important and so thoroughly confirmed that it was awarded the Nobel Prize, and it forced us to admit that the universe is dominated by something we did not know was there. We call that something dark energy, and the name is mostly an admission of ignorance. We do not know what it is. We know what it does, which is to push space apart, to make the expansion accelerate, and we know roughly how much of it there is, which is staggering. When you add it all up, dark energy makes up about 68% of everything in the universe. All the matter, every star, every galaxy, all the gas and dust and dark matter combined accounts for only about 32%. The overwhelming majority of the universe is this invisible, something whose only known effect is to drive space to grow ever faster. And that accelerating growth is going to do something to the sky that is, when you understand it fully, one of the loneliest facts in all of physics. Before we follow that loneliness to its end, it is worth pausing on what this dark energy might actually be, because the answer decides how the whole story finishes. The simplest possibility is that dark energy is a property of empty space itself, a fixed, unchanging amount of energy woven into every cubic centimeter of the vacuum, the same yesterday, today, and forever. Physicists call this the cosmological constant, and if it is correct, then the expansion will keep accelerating at a steady, predictable rate for all of eternity. But the simplest possibility is not the only one, and in the last few years, some careful surveys of millions of galaxies have only hinted, that dark energy might not be perfectly constant after all, that it might be slowly changing in strength over cosmic time. The measurements are not yet conclusive, and the question is very much open. I raise it because it matters enormously for our story. The fate of light at the end of time depends directly on the behavior of dark energy, and that behavior is something we are still, right now, with telescopes operating tonight, trying to pin down. The ending of the universe is not yet fully written in our equations. A single number, still being measured, decides which version of the ending actually comes to pass. Here is what it does. When space expands at a steady rate, distant galaxies recede from us, but their light can still, with enough patience, cross the growing gap and reach us eventually. But when the expansion accelerates, when the gap between us and a distant galaxy grows faster and faster, a threshold is crossed. Beyond a certain distance, the space between us and a faraway galaxy is stretching so quickly that the galaxy's light can never close the gap. The light sets out toward us, moving at the speed of light as always, but the space it has to cross is growing faster than the light can cover it. The light falls behind, forever. It will never arrive. That galaxy has crossed what we call the cosmic event horizon, and once it does, it is gone from our reach completely. Not just hard to see, impossible to see, ever again, no matter how long we wait. And the accelerating expansion is pushing galaxies across that horizon, one after another, continuously, like a tide going out. Right now, with powerful telescopes, we can see many billions of galaxies scattered across the observable universe. But that number is not going to grow, it is going to shrink. As the expansion accelerates, the galaxies we can currently see are, one by one, being carried past the event horizon, their light redshifted longer and longer until it fades from any possible detection, and then carried beyond reach entirely. The sky is emptying, slowly, over enormous spans of time, but relentlessly, the universe is removing its own contents from view. If you follow this forward, the consequences become quietly devastating. In roughly 100 to 150 billion years, every galaxy outside our own immediate neighborhood will have crossed the event horizon and vanished. Our galaxy, and the small group of galaxies gravitationally bound to it, will by then have merged into a single large galaxy, held together by their own gravity, immune to the expansion that only acts on the largest scales, and that merged galaxy will be utterly alone. Beyond it, in every direction, there will be nothing visible at all. No other galaxies, no distant lights. Just an empty, black sky surrounding a single island of stars, with the rest of the universe still out there, still real, but forever beyond sight and beyond reach. That single island of stars is, in fact, our own future. Our galaxy and the great spiral of Andromeda, along with a few dozen smaller companion galaxies, are bound to each other by gravity tightly enough to resist the expansion that only takes hold on larger scales. Over the next several billion years, our galaxy and Andromeda will fall together, collide, and slowly merge into a single enormous galaxy. That merged galaxy is the island that will remain. Everything beyond it, the billions of other galaxies that currently fill our telescopes, will drift across the cosmic horizon and vanish, one by one, their light stretched away into undetectable redness. What is left behind is one galaxy, alone in a darkness, with no visible edge and no visible neighbor, sailing on through an emptiness that gives no sign of the immense, populated universe it was once a part of. I want to pause on what this means for any thinking creature that might exist in that far future, because it is one of the most unsettling ideas I know. Imagine astronomers living in that lonely far future galaxy, 100 billion years from now, looking out at their sky. They would see their own stars, their own galaxy, and beyond it, perfect darkness. They would have no way of knowing that the universe was once filled with billions of other galaxies. They would have no way of discovering the expansion, because there would be nothing left in the sky to observe receding. They would have no way of finding the first light, because by then it would be stretched far too long and cold to detect. The entire history we are discussing tonight, the expansion, the other galaxies, the very beginning of the universe, all of it would be permanently hidden from them. They would look out and reasonably conclude that their single galaxy, surrounded by infinite empty darkness, was the entire universe, eternal and unchanging. They would be profoundly, unavoidably wrong, and there would be no possible way for them to ever find out. We happen to live in a narrow window of cosmic time when the universe is still young enough, still full enough, still bright enough, that its history is written across the sky for anyone with the right instruments to read. That window is closing. The information is being deleted, and the light is the first thing to go. So as the sky empties, what happens to our photon, the first light, still traveling, still stretching? It keeps fading, of course, but now we can follow that fading toward its true conclusion, because the same accelerating expansion that is carrying the galaxies out of view is also stretching the first light toward the point where it, too, slips beyond detection entirely. The oldest light in the universe is on its way to becoming invisible. Let us follow it there. Part 6. The first light fades to a whisper. We left our photon, arriving at a detector after nearly 14 billion years, stretched from a hot orange glow down to a cold microwave whisper at about 2.5 degrees above absolute zero. But the photons that reach us now are only the ones that happen to arrive at this particular moment in cosmic history. The first light is still out there, filling all of space, and it is still being stretched, still cooling, still fading. The process that brought it from 3,000 degrees down to nearly absolute zero is not finished. It has barely begun, when you measure against the spans of time still to come. So, let us follow the first light forward now, past our own era, into the future, and watch what becomes of it. The expansion is accelerating, which means the stretching of every photon's wavelength is not just continuing, but speeding up. Today, the first light glows, if you can call it that, in the microwave band, with a wavelength of about 1 millimeter and a temperature of just under 3 degrees above absolute zero. Give it time, and the universe will keep pulling that wave longer. Its temperature will keep falling toward 2 degrees above absolute zero, then 1, then a fraction of a degree, then a fraction of a fraction, never quite reaching the absolute zero it is always approaching, but getting unimaginably close. As that happens, the character of the first light changes. The wavelength, about a millimeter today, will be stretched to centimeters, then to meters. The first light will pass out of the microwave band and into what we would call radio waves, waves so long and so faint that detecting them would require instruments of a scale we can barely imagine. Keep going, and the wavelengths grow longer still, to the length of a room, then a building, then a city. There will come a time when a single wave of the first light, from one crest to the next, is longer than a planet, then longer than the distance between planets, then longer than the distance between stars. The wave keeps stretching because the space keeps growing, and there is nothing to stop it. And here we arrive at a genuinely strange threshold, one that deserves a moment of careful attention. As the expansion accelerates, there is a limit to how large a region we can ever observe or interact with, set by that cosmic event horizon we met in the last part. It defines a kind of bubble of reachability around any observer. Now think about what happens when the wavelength of the first light is stretched until it becomes as long as that bubble itself, and then longer. A wave that is larger than the entire observable region can no longer really be detected as a wave at all. There is not enough accessible universe left to contain even a single crest-to-trough swing of it. The first light, in effect, stretches itself out of existence as something observable. It does not vanish. The photons are still there, still real, still indestructible, still moving at the speed of light. But they have been drawn out so impossibly long, so faint, so cold, that nothing anywhere could ever detect them, absorb them, or be warmed by them. They become, in the most complete sense, invisible. Let me make the scale of this stretching as concrete as I can, because the numbers themselves carry the feeling. Today, a single wave of the first light, from one crest to the next, is about a millimeter long, roughly the thickness of a credit card. As the ages pass and space keeps expanding, that wave will be stretched to the length of your hand, then the length of a room, then the height of a mountain. Keep going, and a single wave grows longer than the diameter of a planet, then longer than the distance from a planet to its star, then longer than the distance between neighboring stars. Eventually, in the far future, one wave of the first light will be stretched longer than the entire distance across what we can now see of the universe. And a wave that is larger than the universe that contains it cannot really exist as a wave at all, because there is no longer room for even a single full swing of it. The first light does not so much disappear as outgrow the cosmos it travels through, stretched past the point where the word light still has any practical meaning. This is the fate of the first light, the oldest thing in the universe, the relic glow of the beginning, the light that has been faithfully carrying the image of the cosmos's infancy across nearly 14 billion years, will be stretched by the accelerating expansion until it is colder than any cold we can name and longer than any instrument could ever catch. The baby photo of the universe will not be torn up or burned. It will simply fade, gradually and completely, until there is no one and nothing left that could ever develop it. And the window in which that photo can still be read, the window we happen to live inside, is finite. A few 100 billion years from now, the first light will be undetectable in principle, not just in practice. The beginning of the universe will have become permanently unknowable. There is a phrase I want to give you now, and I want you to hold on to it, because we are going to come back to it more than once before tonight is over. Light never dies. It only fades. The first light is showing us exactly what that means. Those ancient photons are not dying as they cool toward absolute zero. They cannot die. They have no mass to lose, no clock counting down, no mechanism of decay. Every single one of them is as indestructible as the day the fog lifted. And yet they are fading toward a coldness and a faintness so complete that they might as well be gone, even though not one of them has actually ceased to exist. This is the central strangeness of the entire story. The end of light is not a death. It is a fading so total that it becomes indistinguishable from absence, while never actually being absence at all. I find this oddly comforting in the small hours, and I will tell you why. We are used to thinking that things end by being destroyed, that the way to be gone is to be broken apart and scattered. But the first light teaches a gentler and stranger lesson. It is possible to fade without ever being destroyed. It is possible to become unreachable, undetectable, lost to the universe, while remaining, in your own quiet way, perfectly intact. I think this is why the fading of the first light feels less like a tragedy than you might expect when you really sit with it. Nothing is being broken, nothing is being torn apart or burned away. The relic glow of the beginning is simply being carried by the patient growth of space into a stillness so complete that the universe can no longer perceive it. It is a little like a sound that does not stop but only grows quieter and quieter past the threshold of hearing, still ringing in some sense, but no longer heard by anyone. The first light goes on. It just goes on alone. In a register, the cosmos has grown too large and too cold to read. Somewhere out there, right now, the photons of the first light are still flying, still carrying the faint imprint of the beginning, growing colder and longer with every passing age, and they will keep doing so long after the stars are gone. They are not dying, they are only fading, and the stars, it turns out, are about to do something similar, though their version of it is more dramatic and far more final feeling than the slow cooling of the first light. Because the next thing that happens, on this long walk into the future, is that the lights begin to go out. Part 7. The stars go out. We have spent a long time with the first light, the faint background glow of the beginning, and now we need to turn our attention to the other kind of light, the kind you actually think of when you hear the word. The light of stars, the light of the sun. The bright, warm, generous light that lets you see, that grows the plants, that fills the day and dots the night. This is the light that feels most alive to us, most permanent, most like a fixture of reality. And it is, of all the light in the universe, the most temporary. The age of starlight, which feels eternal to us, is in fact a brief opening chapter, and it is going to end. To see why, you have to understand where starlight comes from. A star is a tremendous ball of gas, mostly hydrogen, held together by its own gravity, so heavy that the pressure and heat at its center are enough to force atomic nuclei to fuse together, releasing energy. That energy, working its way out from the core and finally streaming off the surface, is starlight. Every photon of sunlight that has ever warmed your face was made in the fusing core of the sun and took a long, slow journey to the surface before flying free. But this process depends on fuel. A star can only shine for as long as it has hydrogen, or other elements, to fuse. When the fuel runs out, the star dies. And there is only so much fuel in the universe. The universe has a finite supply of gas from which to make stars, and every generation of stars uses some of it up. Some of that gas is returned when stars die and shed their outer layers, but not all of it, and each cycle locks more and more matter away in dead stellar remnants that will never fuse again. So star formation, across the whole universe, is a process with an end. It has, in fact, already peaked. The universe formed stars most furiously billions of years ago, and the rate has been declining ever since. We are living in the long, slow afternoon of star formation, well past its noon. The gas is gradually being used up, and one far future day, the last star that will ever form will form, and after that, no new stars will ever be born again. The stars that already exist will continue to shine for a while after that, each for its own lifespan, and here the universe shows a strange kind of mercy in how it ends the age of starlight. The biggest, brightest, hottest stars burn through their fuel fastest, living and dying in just a few million years, a blink. The smaller a star is, the longer it lasts, because it burns its fuel slowly and sparingly. And the longest-lived stars of all are the smallest, the faint red dwarfs, stars so modest and economical that a single one can keep burning, dimly and steadily, for 10 trillion years or more. To put that span in perspective, the universe is currently less than 14 billion years old. A red dwarf can shine for 10 trillion years. That is nearly 1,000 times the entire current age of the universe. The smallest, faintest, least impressive stars are the ones that will outlast all the others, glowing on in the gathering dark long after every brilliant blue giant has died. It is worth pausing on our own star for a moment, both because it is home and because it is the source of a very common confusion. Our sun is an ordinary, middle-sized star, and it has been shining steadily for about 4.5 billion years. In roughly 5 billion more years, it will run low on the hydrogen fuel in its core, and in response, it will swell enormously into a red giant, large enough to swallow the inner planets, before shedding its outer layers in a slow, glowing exhalation and collapsing into a white dwarf, a dense, Earth-sized ember that will spend the next ages cooling in the dark. That is the death of our sun, and it is genuinely the end of the only light most of us ever think about. But it is crucial to see that the death of the sun is not the end of light. It is the end of one ordinary star, one among hundreds of billions in our galaxy alone, and hundreds of billions of galaxies beyond. When people imagine the end of light, they often picture the sun going out, but the sun's death, 5 billion years from now, is barely the beginning of our story. Long after the sun is a cold white ember, other stars will still be shining, and new stars will still be forming, and the smallest red dwarfs will go on burning for trillions of years more. The end of starlight is not the death of any single star. It is the day, almost unimaginably far beyond the death of our sun, when the very last star of all finally goes dark. So the age of starlight does not end suddenly. It dims. First the great bright stars go, in their brief and violent fashion. Then the medium stars, the suns like ours, swell and shed their outer layers and collapse into slowly cooling embers. And finally, across spans of trillions of years, the red dwarfs, the last holdouts, fade one by one, until at last there comes a moment, an unthinkably far future moment, when the very last star in the universe flickers and dims and goes out. After that moment, never again will there be a newborn star anywhere in the cosmos. The age of starlight will be over, having lasted, in the end, only the first 100 trillion years or so of a universe that has eternity ahead of it. Let me take you to that final moment, because I think it deserves to be witnessed. Imagine standing on the cold surface of some world, trillions upon trillions of years from now, in a galaxy that has long since stopped making stars. The sky above you is almost completely black. There are no bright stars left, no familiar constellations, none of the thick scatter of light we see on a clear night today. There is only one point of light remaining in the whole sky, a single dim red ember, low and faint, the last red dwarf, the final star in the universe still burning. It has been glowing like this, slowly and patiently, for 10 trillion years, sipping at the last of its fuel. And now, as you watch, it begins to fade. The red light deepens, dims, contracts. It flickers the way a coal flickers at the very end, and then, quietly, with no explosion and no sound, it goes dark. The last star is gone. And the universe, for the first time since the first stars ignited, contains no starlight at all. The galaxy around you is now lit by nothing but the cooling embers of the dead, and the dark is absolute in a way it has never been before. It would be natural to think that this is the end of our story, that with the last star gone, the universe simply falls into eternal, total darkness, and there is nothing more to say. But that is not what happens. The end of starlight is not the end of light. The universe still has light left in it, fainter and stranger light. Light that comes not from burning stars, but from the slow processes of dying matter and the unexpected glow of the darkest objects that exist. The age of stars is over, but a long, dim twilight is just beginning, and there are still things in the dark that shine. We have to follow the light into that twilight now, into an era so long and so cold that everything we have discussed so far will come to seem like the brief, bright morning of the universe. Part 8. The Long Twilight. After the last star goes out, the universe enters an era so long that it is genuinely difficult to hold in the mind. Scientists who study the far future have a way of measuring these spans, using powers of 10, because ordinary numbers fail completely at these scales. The age of stars, the era we have been living through, lasts until about 100 trillion years after the beginning. The era we are entering now, which we can call the Long Twilight, stretches from there out to a number so large I can only write it as 10, followed by 40 zeros of years. We are leaving behind the brief morning of the cosmos and walking into its endless, dim afternoon, an afternoon that lasts far longer than everything that came before it combined. I want to give you a way to feel the size of these numbers, because written down they slide past the mind too easily. The era of stars, which feels to us like the whole of cosmic history, lasts roughly 100 trillion years. The long twilight we are now entering lasts until a 1 followed by 40 zeros of years. To get a sense of the gap, imagine compressing the entire era of stars, all 100 trillion years of it, every star that ever shone, down into a single second. On that scale, the long twilight would not last a minute or an hour or a year. It would last for spans still measured in powers of 10 so large that no ordinary unit of time could contain them. The bright, star-filled chapter of the universe, the only chapter we have ever known, the chapter containing every sunrise and every life and every history that has ever happened or ever will, is a single brief flash at the very beginning of a darkness that goes on almost without end. We are not living in the middle of cosmic time. We are living in its first bright, fleeting morning, and almost all of time lies in the dim and cooling afternoon ahead. What is the universe like in this twilight? The stars are gone, but their corpses remain, and the universe is now a graveyard of stellar remnants drifting slowly through the dark. There are white dwarfs, the cooling cores of stars like our sun, each one about the size of the Earth but packed with the mass of a star, glowing faintly with leftover heat. There are neutron stars, the collapsed cores of larger stars, impossibly dense, a whole sun's worth of material crushed into a ball the width of a city. There are black holes, which we will come to soon. And there are countless brown dwarfs, objects that never quite became stars, too small to fuse hydrogen, drifting cold and dark through the emptiness. This is the population of the twilight universe. Not living stars, but their remains, scattered thinly across galaxies that no longer shine. These remnants are not entirely dark, not at first. A freshly formed white dwarf is still hot, glowing with the leftover heat of the star it used to be, and it will keep glowing for an enormous span of time as it slowly cools. But cool it does, inexorably, radiating its warmth away into the surrounding dark, growing dimmer and redder and colder over the ages, until eventually, after perhaps a quadrillion years or more, it fades to a cold, dark, dead ember, what we call a black dwarf, an object that has finally exhausted the last of its heat and gone completely dark. The universe of the long twilight is slowly filling up with these black dwarfs, the truly cold corpses of stars, no longer giving off any light at all. So where does light come from in this era, if the stars are dead and even their embers are going cold? It comes from rare and quiet events, scattered thinly across the immense dark. Once, in a very long while, two of these dead remnants, drifting through a dead galaxy, will happen to collide, and the collision will briefly flare with light and even, sometimes, reignite a spark of fusion, a brief false dawn before darkness returns. Once in a long while, matter will fall onto a black hole or a neutron star and heat up enough to glow for a time. But these are isolated incidents, separated by spans of time so long that the universe as a whole is, to any observer, simply dark. The light of the twilight is not a steady glow. It is the occasional, lonely flicker of an accident in an enormous black room. There is one more possible source of light in the long twilight, and it is one of the strangest, because it comes from matter itself slowly falling apart. The ordinary matter that everything is made of, the protons at the center of every atom, may not be perfectly stable. Some of our best theories of physics predict that a proton, given enough time, will eventually decay, breaking down into lighter particles and releasing a small amount of energy as it goes. We have never actually observed this happening. We have watched enormous tanks of water for years, waiting to catch even a single proton in the act of decaying, and we have never seen one, which tells us that if protons do decay, they do so only after an almost incomprehensibly long time, longer than 10,000 trillion years on average. But in the long twilight, there is nothing but time. And if protons do decay, then across these immense spans, the dead remnants of stars, the black dwarfs and neutron stars, will very slowly evaporate, their matter trickling away particle by particle, each tiny decay releasing a faint flicker of energy. To get a sense of how faint this glow truly is, consider the numbers physicists have estimated for it. A dead star, an entire collapsed sun's worth of mass, slowly evaporating through this trickle of proton decay, would shine with a power of only a few hundred watts. Let that sink in for a moment. A whole star, all of its enormous mass, glowing as dimly as a couple of household light bulbs. The lamp in your room tonight may well be brighter than an entire dead star will be, ages from now, in the long twilight. That is the scale of the dimming we are talking about. Not darkness exactly, but a light so faint that the comparison to anything in your everyday life almost breaks down, a whole sun reduced to the output of the bulb beside your bed. The picture this paints is almost unbearably quiet, and I want to let it be quiet for a moment, the way the era itself is quiet. Imagine the universe in the long twilight, hundreds of trillions of years from now and beyond. The galaxies still exist, loosely, but they no longer shine. They are immense, slow-turning collections of dead stars, black dwarfs, and cold neutron stars and brown dwarfs, drifting through a darkness lit by almost nothing. Here and there, separated by spans of time longer than the entire age of the universe today, a faint flicker, a collision, a flash of falling matter, a whisper of energy from a decaying proton, and then darkness again. The whole cosmos is settling, cooling, growing quieter and dimmer and colder, like a great house in which all the lamps have been put out one by one and only the faintest embers remain in the grates, ticking softly as they cool. This is the long afternoon of the universe, and it lasts almost forever, and through all of it, light grows steadily rarer and fainter. And yet, even here, even in this dim and cooling graveyard, the universe is not done producing light. Because there is one kind of object left, the most extreme object that exists, that we have not yet accounted for. We think of it as the darkest thing in the universe, a place from which light cannot even escape. And yet, against all intuition, it turns out that these objects are not perfectly dark after all. In the long ages of the twilight, after even the black dwarfs have gone cold, it is the black holes, of all things, that become the last sources of light in the cosmos. To understand how the darkest objects in existence end up giving the universe its final light, we have to look closely at what a black hole really is, and at one of the most surprising discoveries in the history of physics. Part 9. The Last Lanterns. A black hole is what remains when a great deal of matter collapses under its own gravity into a region so dense that nothing, not even light, can escape from it. This is the part everyone knows. A black hole has a boundary called the event horizon, and once anything crosses that boundary, it can never come back out, because escaping would require moving faster than light, and nothing can do that. Light that falls in does not come back. Light that gets too close is swallowed. For this reason, black holes have always been understood as the ultimate sinks, the darkest objects in the universe, places where light goes to disappear and is never seen again. The very name tells you what they are. Black holes, absence made into an object. So, it comes as a genuine shock, one of the great surprises in the history of physics, to learn that black holes are not perfectly black at all. They glow, faintly, almost imperceptibly, but they glow, and given enough time, they glow themselves entirely out of existence. This discovery was made in the 1970s by the physicist Stephen Hawking, and it was so unexpected that he himself spent a long time checking it before he believed it. What he found, by combining the physics of gravity with the physics of the very small, the quantum world, was that the event horizon of a black hole is not a perfect one-way door. A subtle quantum process at the very edge of the horizon causes the black hole to slowly emit particles, including particles of light drifting away into space. This faint emission is now called Hawking radiation, and it changes everything about the long-term fate of black holes and about the fate of light at the end of time. The way Hawking radiation works is subtle, and any short description is a simplification. But here is the essence of it. Empty space, according to quantum physics, is not truly empty. It constantly seethes with pairs of particles flickering into existence and then annihilating each other almost instantly, so quickly that they are normally undetectable. These are sometimes called virtual particles. Now imagine such a pair flickering into existence right at the edge of a black hole's event horizon. Occasionally, before the pair can annihilate and vanish, one of the two falls across the horizon into the black hole, while the other escapes outward into space. The escaping particle is now real, carrying away a tiny bit of energy, and because energy and mass are equivalent, the black hole, which supplied that energy, loses a tiny bit of its mass. Repeat this over and over, across enormous spans of time, and the black hole slowly, steadily evaporates, radiating its mass away as a faint trickle of particles and light. There is a profound puzzle buried in this slow evaporation, one that has occupied physicists for half a century and is still not fully resolved. Everything that ever fell into a black hole, every star it swallowed, every planet, every particle, carried with it a great deal of information about what it was. According to the deepest principles of quantum physics, that information can never truly be destroyed. And yet, if a black hole slowly radiates away into a faint, featureless drizzle of particles and finally vanishes entirely, where did all that information go? Does the escaping radiation somehow carry it out, encoded in subtle patterns we do not yet know how to read, so that the last light of an evaporating black hole is in some sense the entire history of everything that ever fell in, streaming back out into the universe? Or is the information genuinely lost when the black hole disappears, in violation of rules we thought were unbreakable? This is the famous black hole information puzzle, and it sits right at the boundary between gravity and the quantum world, exactly where our current understanding runs out. Whatever the final answer turns out to be, it gives the last light of the black hole era a strange new weight. That faint final glow may be carrying away, in a form we cannot yet decode, the encoded memory of everything the darkness ever consumed. There is a strange and important detail here, and it runs exactly opposite to your intuition. The smaller a black hole is, the hotter it is, and the faster it radiates. The largest black holes are the coldest and the slowest to evaporate. The temperature of a black hole's glow is inversely related to its mass. A black hole with the mass of our Sun has a temperature of only about 60 billionths of a degree above absolute zero, which is far colder than the universe is even now. The supermassive black holes at the centers of galaxies, with millions or billions of times the Sun's mass, are colder still, almost inconceivably faint. This has a curious consequence for the timing of everything. Today, black holes are actually colder than the cosmic microwave background still bathing the universe, which means they currently absorb more energy from that background glow than they radiate away. They are not yet evaporating at all. They cannot begin to truly evaporate until the universe has cooled enough, until the first light has faded enough that the black holes are finally warmer than their surroundings. Only then, in the far future, after the long twilight, can they begin to give back their mass to the universe. And when they do, the spans of time involved are staggering, even by the standards of this story. A black hole with the mass of our Sun would take about 10 to the 67th power years to fully evaporate. That is a 1, followed by 67 zeros. The supermassive black holes, the giants at the cores of galaxies, take far longer still. The largest of them, with the mass of tens of billions of suns, would take something like 10 to the 100th power years to finally radiate away completely, a 1 followed by 100 zeros, a span of time so long that it makes the entire history of the universe so far, all 14 billion years of it, look like nothing at all, less than a single tick of a clock. These black holes are the most patient objects that will ever exist. It is worth dwelling on what these spans of time actually mean, because the mind slides right off them otherwise. The entire history of the universe so far, from the beginning through the formation of galaxies and stars and planets and every living thing, amounts to 14 billion years. The time it takes the largest black holes to evaporate is a 1 followed by 100 zeros of years. If you tried to write that span as a multiple of the universe's entire current age, the multiplier would still be a number with more than 80 zeros in it. Against that, everything that has ever happened, all of cosmic history to this point, is not even a rounding error. It is less than the first instant. The black holes will sit there, barely glowing, for so long that the whole bright story of the universe we know will have been over almost since the very beginning of their wait. They sit in the emptying dark, barely glowing, slowly giving themselves back to the universe across spans of time that defy every attempt to imagine them. But evaporate they do, and here is the part that matters most for our story. As a black hole loses mass, it gets smaller, and as it gets smaller, it gets hotter, and as it gets hotter, it radiates faster. The process feeds on itself. For almost the entire lifetime of a black hole, the evaporation is unimaginably slow and faint. But near the very end, when the black hole has shrunk down small, the runaway takes over. The radiation grows more and more intense. The black hole hotter and hotter, brighter and brighter, until in its final moments it flares, releasing the last of its mass in a brief, brilliant burst of high-energy particles and light, and then, abruptly, it is gone. After ages of patient, near-invisible fading, the black hole ends not with a whimper, but with a flash. A final pulse of light into the surrounding dark, the last bright event that region of the universe will ever produce. I want you to witness one of these, because it is, quite literally, among the last bright things that will ever happen. Picture the universe unthinkably far in the future, past the long twilight, far into the era when black holes are the only significant structures left. The galaxies are gone, dissolved, their dead stars long since decayed or scattered. Space is colder and emptier than anything we have words for. And in all that darkness, there is one black hole left, the last one, the most massive and therefore the most patient of them all, which has been slowly evaporating for something like 10 to the 100th power years. Now, at last, it is reaching its end. It has shrunk over the eons, and it is growing warmer and brighter. The faint glow that has surrounded it for ages begins to intensify. It quickens. The radiation pours off faster and faster, the object blazing now in the absolute dark, the first real light in this region of space for spans of time beyond counting. And then, in its final instant, after an almost eternal life, it flares, a last burst of light and particles flung outward into the emptiness, brighter than anything has been in ages, a final flame in a universe of dark. And then it is gone, and the light from that last flash streams outward, the final fresh light the cosmos will ever make, racing away into a darkness that now has nothing left in it to shine. There is something almost unbearably poignant in this, and I do not want to rush past it. The black holes, the darkest objects in all the universe, the very places we think of as where light goes to die, turn out to be the last things in the cosmos that give light. Long after the stars are dead, long after even their cold corpses have decayed, it is the black holes, glowing ever so faintly, and then, at the very end, brilliantly, that serve as the universe's final lanterns. The darkest things become the last to shine. There is a lesson hidden in that reversal, and it is the kind of thing this channel was made to notice. We spend the whole of our lives sorting the universe into things that give light and things that take it away, into the bright and the dark, the living and the dead. And then, at the very end of the story, the categories quietly trade places. The stars, which seemed like the eternal givers of light, run dry and go out. The black holes, which seemed like the pure devourers of it, become the final faithful sources. Nothing in the universe, it turns out, is permanently one thing or the other. Given enough time, the brightest things fall silent, and the darkest things begin, softly, to glow. The objects defined entirely by their ability to swallow light spend the final ages of the universe slowly giving it back, until the very last one flares and fades, and there are no lanterns left at all. After that final flash, the universe will never again produce a single new photon from any star, any remnant, any black hole. The age of light-making is over. Everything that happens after this, every photon that still exists, is light that was made before, still travelling, still fading, in a cosmos that can no longer make any more. We have to follow the light into that final era now, the era after the last lantern goes out, and ask the question this whole journey has been building toward. When there is nothing left to make light, and nothing left to absorb it, what happens to the light that remains? Part 10. The Dark Era and the Floor of Cold. We have now arrived at the final era of the universe, the one that comes after the last black hole has evaporated, and it has a fittingly plain name. We call it the Dark Era. It begins somewhere beyond 10 to the 100th power years from now, and, unlike every era before it, it does not end. The stelliferous age of stars lasted 100 trillion years and ended. The long twilight of dead remnants lasted far longer and ended. The age of black holes lasted longer still and ended. But the Dark Era does not give way to anything else. As far as physics can currently tell, it simply continues, forever, and whatever is in it at the beginning is, more or less, what will be in it for all of eternity afterward. So what is in it? And crucially, what light is in it? By the dawn of the Dark Era, the universe has been emptied of nearly everything we would recognize. The stars are gone, the galaxies are gone, the dead stellar remnants have decayed away, their protons long since crumbled. The black holes have evaporated, down to the very last one. What remains is the thinnest imaginable soup of leftover particles, scattered across distances so enormous that any two of them might be separated by more than the size of the entire observable universe today. There are stray electrons and their antimatter twins, positrons, drifting alone. There are neutrinos, ghostly particles that barely interact with anything, streaming through the void. And there are photons, light. The accumulated light of the entire history of the universe. Every photon that was ever emitted and never absorbed, still out there, still moving at the speed of light, still being stretched longer and colder by an expansion that never stops. This is the light at the end of time, and I want to describe its condition carefully, because it is the answer to the question we began with. These final photons are unimaginably stretched. The expansion has been pulling their wavelengths longer without pause for an eternity, and so they have wavelengths beyond any scale we can meaningfully picture, far longer than the distance between the few scattered particles left in space, perhaps longer than what was once the entire observable universe. Their energy has been drawn down so far towards zero that they are colder than any cold that has a name. And they are spread so thinly, across such enormous and ever-growing volumes, that the chance of one of them ever encountering anything that could absorb it is, for all practical purposes, none. They simply travel, forever, through an emptiness that grows forever, fading forever, and never, ever stopping. And now we can finally face the question directly: does light ever truly die? After everything, after the first light, and the stars and the lanterns of the black holes, after 100 orders of magnitude of years, do the last photons finally wink out, cease, end? And the answer, the strange and quiet answer this whole journey has been carrying toward you, is no, they do not. They cannot. A photon, you will remember, has no mass, does not age, and does not decay. There is nothing inside it to run down. There is no mechanism by which it can simply stop existing on its own. So the final photons of the dark era do not die. They fade endlessly, their wavelength stretching toward infinite length, and their energy sinking toward zero, getting closer and closer to nothing with every passing age, but never actually arriving at nothing, never actually reaching the zero they forever approach. Light never dies, it only fades. We said it early tonight, almost gently, as a small comfort about the lamp in your room. Now you can feel its full and final weight. The end of light is not an event. It is an asymptote, an endless approach to a nothing that is never quite reached. If you want a picture to hold on to, imagine a single struck note, the last note of a piece of music, allowed to ring out and never stopped. It does not end on a sudden silence. It simply grows fainter and fainter and fainter, the sound thinning toward a quiet that it approaches forever without ever fully arriving. There is always, in principle, a little less of it, and never quite none of it. That is what the last light of the universe is like. The final photons ring on through the growing dark, their waves stretching longer and their energy sinking lower, getting nearer and nearer to nothing across spans of time without end, and yet never crossing the line into true non-existence. The universe does not switch off its last light. It only turns it down, forever, toward a silence it never completely reaches. There is one last subtlety here, and it is a beautiful one, because it means the dark era is not perfectly, absolutely black after all. Remember that the universe's expansion is driven by dark energy, and that this gives the cosmos a kind of horizon, a limit to what any observer can reach. It turns out that such a horizon is not entirely silent. In much the same way that a black hole's event horizon gives off a faint Hawking glow, the cosmic horizon of an expanding, dark energy-dominated universe gives off its own incredibly faint radiation, a whisper of light produced by the horizon itself. The temperature of this whisper is almost beyond belief in its smallness, around a few 100 billion billionths of a degree above absolute zero, far colder than anything we have discussed, but it is not zero. And as far as we can tell, this faint horizon glow never goes away. It is the permanent temperature floor of the universe, the irreducible minimum, the last and lowest light there is. Long after every star and every black hole is gone, the empty universe will still be bathed in this almost nothing glow, a final, eternal, immeasurably faint radiance that the cosmos can never quite extinguish. I find a strange peace in that detail, and I will tell you why before we move on. We began tonight imagining that the end of light would be a falling into total, absolute, perfect darkness, a complete and final blackness. But that is not what physics describes. The universe never quite manages to turn the lights all the way off. There is always that faint flaw of cold radiation, that whisper from the horizon, never bright, never warm, but never zero either. The end of light is not darkness. It is the dimmest conceivable glow, holding steady forever, in an empty universe that has run out of everything except the faintest possible light. The cosmos does not end in blackness. It ends in a glow too faint to see, that nonetheless never goes out. I have been describing one version of the ending, the gentle one, the slow fade into an eternal, almost nothing glow. But I owe you the honest admission that this is not the only possibility, and which ending actually happens depends on that open question about the true nature of dark energy. The gentle fade is what unfolds if dark energy is a true cosmological constant, holding steady forever. But if dark energy were instead to grow stronger over time, without limit, the story would end very differently and far more violently. In that case, the expansion would not merely accelerate but run away completely, faster and faster, until it tore the universe apart in a finite span of time, an event some physicists have called the Big Rip. First, the most distant galaxies would be ripped from view, then our own galaxy would be pulled apart, then solar systems, then planets, and finally, in the last fraction of a second, individual atoms would be torn apart, and even the wavelengths of light itself would be stretched to infinity all at once. In one such model, this catastrophe would arrive some 22 billion years from now, which by the standards of tonight's journey is almost the present moment. In a big rip, light does not fade gently over endless ages. It is torn apart, violently and altogether, with everything else. We do not yet know which of these endings is the real one, the slow fade or the sudden tear, and the difference between them comes down entirely to a property of dark energy that we are still working to measure. The end of light is, even now, an open question. So that is the fate of light at the end of time, told from the outside, from the point of view of the universe. The stars die, the black holes evaporate, and the light that remains fades forever toward a zero it never reaches, in a cosmos lit only by the faintest permanent whisper of its own horizon. It is a quiet ending, a gentle one, an endless dimming rather than a death. But we have been following a single photon this whole time, our photon, the first light, and we have not yet asked what this entire journey looks like from its point of view rather than ours. And when we do, when we finally take the photon's own perspective seriously, the whole story we have just told is going to turn inside out, and the end of time is going to reveal that, for light itself, it was never really there at all. Part 11. The Photon That Never Arrives. We have followed our photon for this entire journey from the outside, watching it as if we were standing beside it, marking off the billions and then the trillions, and then the unthinkable powers of 10 of years as they passed. From that outside view, our photon has had a long and eventful existence. It was born in the clearing fog 380,000 years after the beginning. It crossed a young universe full of forming galaxies. It was stretched and cooled across 14 billion years into a cold microwave whisper. And if it was never absorbed, never caught by an eye or a detector or a grain of dust, It is still out there now, and it will keep going, stretching ever longer and colder, on into the dark era and beyond, fading forever toward a zero it never reaches. From our point of view, that is a history almost too long to comprehend. But our point of view is not the only one, and it is not even, in a certain sense, the truest one. Because we have left out the most extraordinary thing about our photon, the thing we set down carefully near the very beginning of tonight and promised to return to. From light's point of view, no time passes at all. We have been measuring the photon's journey in years, in billions and trillions of years, but those are our years, marked by our clocks, in our frame of reference. The photon does not have those years. The photon has no clock. For the photon itself, the entire journey we have just described, from the clearing fog to the end of time, takes no time whatsoever. Let me make this as concrete as I can, because it is the strangest and most beautiful idea in this whole story, and it deserves to land fully. When something moves at the speed of light, time, for that thing, does not merely slow down, it stops completely. The faster anything travels, the more its own time dilates, stretches, slows relative to the world around it, and at the speed of light, this effect reaches its absolute limit. The interval of time experienced by a photon between any 2 points on its path is exactly zero, not very small, zero. This means that for our photon, the moment it was born in the recombination fog and the moment it is finally absorbed, or fades beyond all detection at the end of time, are not separated by any duration at all. They are the same instant. They touch. There is no gap between them, no journey in between, no long wait, no billions of years of travel. For the photon, emission, and ending happen together in a single timeless flash. I want you to try to take the photon's perspective now as fully as a mind built for time can manage, because this is the scene I most want you to feel tonight. You are the first light. You come into being in the clearing haze of the early universe, and in the very same instant, with no time passing, with no journey at all, you arrive at your ending, wherever and whenever that is, the eye that catches you, or the cold dark trillions of years from now, where you finally fade past all detection. For you, there is no in-between. The forming of the galaxies, the death of the stars, the evaporation of the black holes, the whole immense pageant of cosmic history that we measured out in powers of 10, none of it is something you live through. It all happens, from your perspective, in the gap between two instants that are actually one instant. Your birth at the beginning of everything and your ending at the end of time are pressed together, touching, a single flash that somehow spans the entire history of the universe and yet takes no time at all. This is what it means to say that light does not travel through time the way we do. We experience the universe as a sequence, one moment after another, the years accumulating behind us. The photon does not. The photon experiences its entire existence, however long it lasts, by our reckoning, as a single timeless moment. And this leads to a conclusion so strange that it took me a long time to truly absorb it. There is no end of time for light. The end of time, that far future dark era we work so hard to reach, is something that happens to everything except light. The stars experience their deaths. The black holes experience their slow evaporation. We, if we were somehow there, would experience the deepening dark. But the photon experiences none of it, because the photon experiences no duration at all. The end of time is a destination that everything in the universe is traveling toward, slowly through the years. Everything except light, for which the end of time and the beginning of time are the same single instant, and the journey between them simply does not exist. Consider what this does to the question we started with. What happens to light at the end of time? We have answered it from the outside. The light fades endlessly toward a zero it never reaches, in an emptying universe lit only by the faintest whisper of its horizon. But from the inside, from light's own frame, the question almost dissolves. For light, there is no end of time to arrive at, because light never travels through time toward any end. The photon that we imagined fading forever in the dark era is, from its own perspective, in the very same instant still being born in the bright fog of the early universe. The beginning and the end are not separated for it at all. The most fragile-seeming thing in the room around you, a thin beam of light, turns out to be the one thing in all of existence that the end of time can never actually reach. There is a tenderness in this that I did not expect when I first understood it, and I want to offer it to you plainly. We tend to fear endings because we experience time, because we feel the years passing and know they are finite. But light does not have that fear available to it, because light does not have time. The photon leaving the lamp beside you right now will, if nothing absorbs it, travel until the end of the universe, fading and stretching across spans that terrify the imagination. And it will experience none of that as a passage, none of it as a loss, none of it as a waiting. For that photon, leaving the lamp and reaching the end of everything, are the same instant, a single flash, eternal and timeless and complete. The end of time, for light, is not a place it ever has to go. It was never going anywhere at all. It simply is, all at once, from the first light to the last. There is a way of holding this that I have found brings a kind of calm rather than vertigo, and I offer it to you gently here in the quiet. We spend our lives inside time, watching it flow, feeling each moment arrive and pass and recede behind us, and so we naturally assume that time is simply what reality is made of, the deepest fact about the world. But light shows us that this is not so. Light is just as real as we are, just as much a part of the universe, and it does not live inside time at all. For light, all of its existence is one moment, undivided, the beginning and the end, held together with nothing in between. This means that time, the flow we take to be the most basic feature of everything, is not universal. It is something that happens to objects with mass, to things like us, and not to light. The universe contains at least one kind of thing for which there is no past and no future, only a single, eternal now. And that thing is the most common, the most familiar, the most overlooked substance in your life. The light in the room with you is, in the most literal sense physics can offer, already living outside of time. And this opens the final door of our journey, the strangest idea of all, because if light experiences the beginning and the end of the universe as a single timeless instant, then perhaps the beginning and the end of the universe are not as different, not as separate, as we have assumed. Perhaps, for a cosmos that ends with nothing left in it but light, the end and the beginning are closer than they appear. There is a serious, if speculative, idea in physics that takes exactly this thought and runs with it all the way, and it suggests that the end of light is not an ending at all, but a beginning. To follow it, we have to take everything we have learned tonight and look at it one final time, from the farthest vantage point there is. Part 12. The End That Is a Beginning. We have reached the far end of time, the dark era, where the only light left is the faintest of whispers, fading forever. And we have seen that for light itself, there is no end of time at all, only a single, timeless instant connecting the first light to the last. Now I want to close tonight with the most speculative idea in this whole story, an idea proposed by one of the most respected physicists of our age, because it takes the strangeness of light at the end of time and turns it into something almost like hope. I will be honest and clear that this idea is not established fact. It is a serious proposal, debated and unproven, sitting out at the edge of what physics can responsibly say. But it is grounded in exactly the things we have spent tonight understanding, and it is, I think, a beautiful place to rest. The idea begins with a simple observation about that final, empty, dark era universe. By the time we reach it, There is essentially nothing left but light, the last fading photons, and a few other particles that, like light, have no mass. And here is the curious thing about a universe made only of massless things. Mass is what allows you to measure time and size. A massive particle has a natural clock built into it, a natural scale, a way of marking duration and distance. But a universe with only massless particles in it has no clocks and no rulers. Light, as we have seen, does not experience time. And without anything that has mass, the universe at the end of time has, in a precise mathematical sense, no way to define how much time is passing or how large anything is. The very concepts of scale and duration stop having meaning. The cold, enormous, empty universe at the end of time cannot tell how cold it is, how empty it is, or how much time has passed, because there is nothing left in it capable of measuring those things. Now hold that thought and put beside it a description of the universe at its very beginning. The early universe, before the fog cleared, was unimaginably hot and dense and energetic, and it too was dominated by radiation, by light and other fast-moving particles, with mass playing almost no role in those first instants. The beginning was a place of pure energy and almost no meaningful scale, and the end, as we have just seen, is also a place where scale loses its meaning, a universe of pure light that cannot measure itself. The physicist Roger Penrose noticed that these two states, the hot, dense beginning and the cold, empty end, despite seeming like complete opposites, share this strange feature. Neither of them has any meaningful scale, and he proposed something audacious. He suggested that if you strip away the one thing that makes them seem different, namely the scale that neither of them can actually measure, the end state of one universe becomes mathematically indistinguishable from the beginning state of another. The cold, empty, scaleless end, full of nothing but light, simply becomes the hot, dense, scaleless beginning of a brand new universe, a new beginning, a new expansion, a new first light. In this picture, which Penrose calls conformal cyclic cosmology, the end of time is not a wall and not a void. It is a hinge. The universe does not stop at the dark era. It forgets its own size and age, because there is nothing left in it that can remember those things, and in forgetting, it begins again. The last light of one universe becomes the first light of the next. And the cycle, perhaps, has no beginning and no end, an endless succession of universes, each one ending in a fading sea of light that becomes the bright dawn of the next. Whether or not the cosmos truly cycles in this way, I find that the idea points at something worth carrying with you regardless. We tend to imagine the beginning and the end of the universe as the two most opposite things imaginable, the hot, bright dawn and the cold, dark dusk, as far apart as anything could be. But run the whole story through, and they begin to resemble each other in the one respect that matters most for tonight. Both are made of light, and almost nothing else. The universe opens with light and closes with light, and in between, for a brief and brilliant while, that light is borrowed by stars and worlds and living eyes before being given back to the dark. We happen to be alive during the borrowing. That is the rare and precious part. The light was here before us and will be here long after, but for this one short chapter, it is here with us, and it lets us see. Whether or not this particular idea turns out to be correct, and we genuinely do not yet know, it captures something true about everything we have learned tonight. Light is the thread that runs through the whole of it. Light was there at the first instant. Light is the last thing left at the end. And light, alone among all things, connects the beginning to the end without experiencing any time in between. Let me gather the whole journey now, gently, because we have come a very long way tonight, and you may be drifting, and that is exactly as it should be. We began with the light in your room, the lamp, the screen, the moon, and the quiet assumption that light is ordinary and permanent. We learned that light is made of photons that have no mass, that never age, and that never decay, the most durable things in all of nature. We traveled back to the first light, born in the clearing fog, 380,000 years after the beginning, and we followed a single photon of it forward as the expanding universe stretched it from a hot orange glow into a cold microwave whisper. We watched the accelerating expansion begin to empty the sky, carrying the galaxies one by one beyond reach, and we watched the first light itself fade toward a faintness no instrument could ever catch. We saw the stars run out of fuel and go dark, the last red dwarf flickering out after 10 trillion years. We walked through the long twilight of dead remnants, and we watched the black holes, the darkest things that exist, become the universe's last lanterns, glowing for ages and then flaring out one final time. We reached the dark era, where the last light fades forever toward a zero it never reaches, in a cosmos lit only by the faintest, permanent whisper of its own horizon. And then we turned the whole thing inside out and saw that for light itself, none of this is a journey at all, that the first light and the last light are, from the photon's view, a single, timeless instant, and that the end of time is something light never actually has to reach. So here is the answer to the question we began with, the truest answer I can give you. What happens to light at the end of time? It fades, but it does not die. It is stretched longer and colder than any name we have, but it never ceases to exist. It becomes undetectable, unreachable, lost to a universe with nothing left to catch it, and yet every photon remains as indestructible as the instant it was born. Light never dies. It only fades. And from light's own point of view, there is no end of time at all, only a single eternal flash that runs from the first light to the last, and perhaps, if the boldest ideas are right, around again to the first light of whatever comes next. I want to leave you with this, as you lie there in the soft glow of whatever light is keeping you company tonight. The photons leaving that lamp, that screen, that candle, the ones falling on your skin right now, are members of the same ageless, deathless family we have followed all the way to the end of the universe. They will not age. They will not wear out. If nothing absorbs them, they will travel until the end of everything, fading but never dying, and for them, the whole immense history of the cosmos will pass in a single timeless instant. The most ordinary thing in your room is, it turns out, very nearly eternal, so let it keep you company. Let it fade softly around you as you drift off, and rest easy in the knowledge that the light, the gentle, patient, ageless light, is the one thing the end of time can never quite put out.